Okay, so this is a third example for class 20 of rigid body Newton's second law, rigid body kinetics. So we have a uniform cylinder rod of 36 inches and it weighs 4 pounds. So I've used US units for all three examples so far. Hopefully the last one is in metric. Yeah, sure enough. Okay, good. So it weighs 4 pounds and it hangs freely from a hinge at A. If a force of magnitude 1.5 is applied horizontally to the left, where H is equal to L, determine the angular acceleration of the rod and the components of the reaction at A. So, I'll get a little housekeeping out of the way. I should have done this in the last one too. I'll find what the moment of inertia is about the pinned and, about the center. All right, so that's actually what we're doing this time. So we have 1/12 mass times L squared, and 1/12, the mass is 4 divided by 32.2, and the length of the thing is 36 inches, but we want to make sure we do it in feet. We end up getting 9.317 E minus 2 slug feet squared. So we do the FBD and the IBD. And we get our coordinate axes up here. And sometimes I actually put that on there as well. That's a good idea. All right, so if we're going to put the loads, let's put the loads onto the left-hand side. We're going to have a reaction right up here, and there'll be a possible reaction in the y direction, a reaction in the x direction, the reaction at A in the y direction, and the reaction of A in the x direction. We also have this external load P that equals to 1.5 pounds, but I'll just put it as a P right here. And then we also have the weight acting right there. And let's see, for the acceleration, is it starting from rest? Let's see, does it say that? We should say uniform length when it hangs freely. Okay, so if it hangs freely, I guess we have to assume that it's starting at rest. Being a nice thing for them to say. So that means that all of the acceleration is in the x direction and happening at the center of gravity of this, and that we anticipate it's going to accelerate in that direction. So it's going to be I, and we'll do I alpha right there. Now I'm showing it about the pin, but it's really, it could be, we could draw that like right around here, right? Just so we don't think about it as being about the pin. Something that we could also tell from this, we could also take the kinematics if we wanted to, and note that the acceleration at x is going to be equal to alpha L over 2. So if we take the sum of the moments about point A, and we assume the counterclockwise is positive right here, we're going to set that equal to the sum of the effective moments. The sum of the effective moments. So we take, taking a look at the left-hand side, we have negative P times L, right? Because all the other ones, all the other forces right there about that point A are going to be in line or through point A, so they don't generate a moment. Now, if on the right-hand side, we're going to have negative, because it's going clockwise, I alpha, but then we're also going to have an effective moment of the center, because this mass times acceleration is an effective force, and it will create a moment, and it's also going to be in the clockwise direction. So you go to mass times acceleration, right, ax times L over 2. But we already know this right here, so I'll write this out as a separate step. And by the way, we could probably have gotten rid of all those minus signs because we noticed they're all in there. This ends up being alpha, but L over 2 squared, right? There's an L over 2 right here, and an L over 2 right here. One thing that we might want to point out to you, and I'm actually going to point it out in the next class, like over and over again, but what we just found was we derived the parallel axis theorem, just so you know. So let's take that force of 1.5 and the length of 36 inches, so that's 36 divided by 12 equals, I don't know why I keep these minus signs in here, 9.317 E minus 2 minus 4 over 32.2 and alpha, and 36 divided by 12 divided by 2 squared, and we end up finding that alpha is going to be equal to 12.08 radians per second squared, and that's the answer to part A. Now, if we want to find, we had to assume that the thing started from rest, so the sum of the forces in the y direction were going to actually equal to 0. So now, so they wanted the components, so we could have written that out right there. Right? So in the x direction is what we're really going to end up caring about. I guess I'll write it out. So because I've got plenty of time, it's so easy to write FBD. Let me draw this. I think it's because I write too fast. If I write too fast is when that happens. That's beginning to be my conclusion with the mysterious horizontal line. Okay. Well, I guess I'll put that P and then W. And MAX, and then this guy right here, right? All right, so continuing on in here, the sum of the forces in the y direction equals mass times acceleration in the y direction, but we note that there is no acceleration in the y direction. Therefore, it's equal to 0. If the thing had an angular, if it did have an angular velocity, then there would be. So we write down that RAY minus W equals 0. So RAY is equal to W, which is equal to 4 pounds. And that is an upwards thing right there. And so now we do the sum of the forces in the x direction equals mass times acceleration in the x direction. And we have RAX, right? It's going to the right, negative P, and then negative mass times acceleration in the x direction. Now, remember from the previous thing here, that we could calculate AX is equal to alpha L over 2 right here. So let's write that out, that RAX minus 1.5 is equal to minus 4 over 32.2 for the mass times the acceleration, which is going to be this angular acceleration of 12.08 times our L over 2, which is 36 over 12 over 2. And so we get an RAX equal to, negative 0.75 pounds. So our answers are going to be RAY is 4.00 pounds up, and RAX is 0.750 pounds to the left, because that's what that negative number meant for us. One thing we might want to say, they asked for the reactions right there, so that's why we're going to have this direction. In some classes, they ask what are they ask for the forces that act on the bar at the pin. What are the forces that act on the bar at A? Well, then, by the way, the arrows are going to go backwards. They're direction arrows. So that's the answer to problem part B right there, right? Part B. And this was part A. The end.